Hello everybody, good afternoon. It's a great pleasure to have Professor Marcos Villarreal here. Thank you very much for accepting to participate in our course, Professor Marcos. Professor Marcos holds a Bachelor in Chemistry from Universidad Nacional de Córdoba. He has a PhD in Biophysics also at the Universidad Nacional de Córdoba, and a postdoc in nanomaterials of the INFIQC CONICET. Professor Marcos Villarreal is research at CONICET, Argentina, and professor at the Department of Computational and Theoretical Chemistry at Universidad Nacional de Córdoba. Professor Marcos Villarreal, it's an honor and a pleasure to have you here. Thank you very much.
Well, thank you, Walter, for your presentation. Thank you, everybody, for come to hear my talk. Feel free at any point to stop me and ask questions. I can ask you along the talk. So, well, I am going to present you our latest work. We are working in development of molecular docking methods using artificial intelligence techniques. So what I mean with this title, well, molecular docking, maybe you know about it from the talk of Stephanie last week. And so I will only take 2 slides to explain it. And using artificial intelligence techniques, I mean not the whole package of artificial intelligence, but only taking the techniques, the methods that they use to optimize function that is at the heart of AI. These techniques for optimization are quite powerful, and we are using to develop what it is called a classic scoring function. But the whole picture we are presenting, it can be used to optimize any kind of molecular docking, classical or not classical molecular docking engine. So this is the work that we are doing in collaboration with Rodrigo Quiroga, and we work in the INFIQC, it's a CONICET Institute in the University of Córdoba. So, well, what is molecular docking? Well, molecular docking resolves the problem to find the position that we call the binding mode, the position and orientation of a small molecule, ideally a drug. You can think of it as a drug in a surface of the protein. So when we find the position and the energy, we dock the molecule. So this tool is a classical tool to develop use in the pharmacy industry to develop new drugs. So what is at the heart of molecular docking? At the heart is a global search for a minimum value. In this case, the value is called the function. The function that we try to minimize is the scoring function that is a representation of the energy of the system. It's a model of the energy of the system. And every minimum in this scoring function, as a function of the generalized coordinates, or I mean the different binding modes of the drugs, represented here as different waveframe conformation of the molecule. Represent a different position and a different energy that the drugs can adopt in this complex. So in order to find the best position, we need first to have a good energy function that is a good map of the real binding energy. So how we develop a good scoring function, how we develop a surface that is a good match of the reality. So the first and the most important element that we need to take into account is experimental data. We need to be able to reproduce this data. And this data is the crystal structure of a protein complex with a ligand. Here we have 4 of these. And in a complement experiment, we can determine the experimental binding affinity of this complex. So with a data set that have the coordinates of the complex, the experimental coordinates of the complex, and its experimental binding energy. And this is the first thing that we need to reproduce. So this is will be the data that we need that we use for training. We use also this portion of the data for testing our surface. So the first approach that one usually do is to define the scoring function f, which will be receive the x coordinate of the complex. The parameters of the function will be passed also. Parameters meaning, for example, radii of the atoms or depths on some interaction energy. This is quite general. When we pass these parameters and variables, we obtain the score function, the score of the scoring function, and we assume that this will be a proxy or a very close imitation of the real energy, the real binding energy. So in order for this to work, we will need to minimize the difference between the experimental energy, large E, and the scoring calculated with the scoring function. So this task of this minimization is just a regression. Sorry. With this regression, you adjust these parameters, and you have your system to your scoring function. So this is the classical approach. We do this for different points or different values of experimental energy. Thank you. And okay. No, I'm sorry. I'm sorry. I'm just adjusting the camera. Okay. This is better. I'm sorry about that. So every point, each point here is the experimental energy and the coordinates of one protein ligand complex. So in this way, you can determine the parameters and completely define your scoring function. But what is the problem with this approach? Well, if you will recall to the energy surface, we are just adjusting a single point. We took the energy of the complex and the X-ray coordinates of the complex, and we try to reproduce this point. But as you already saw, and you can think of it, this point that we adjust maybe is not at the minimum, is in is not necessarily at the minimum and not even the global minimum. And we need to be the global minimum. We need, because in the experiment we know that the system goes to the minimum of this function. In this case is the binding energy, but we need to reproduce this. So how do we accomplish this goal? To have this point, the experimental point, to be a minimum of the global minimum of our scoring function. Actually, we only require this compromise. No, we don't need to parameterize the whole scoring function, the whole surface, because as we only seek for the global minimum just having this coordinate as the minimum is enough. We don't care how the surface is above this minimum. It can be any value, actually. So, well, we can adjust the minimum just by imposing that the parameters also have a minimum, define a minimum in this value, at this value of the coordinates. But the difficult part is to make it the global minimum. The global minimum. How we make this for all the example the global minimum. How can we do this in a systematic and unsupervised way? So we need a system, and here we borrow some concept from the AI, and we thought to put it in the realm of the self-supervised learning. So the system actually, and not only self-supervised, but also by how you say self-supervised and with self-generated data. So how we achieve this goal? Well, we are going to parameterize a starting and storing function. We are going to see where are this minimum of this scoring function, and if we find some situation like this where we need to find a minimum in the red dot, but we have actually our scoring function is the minimum in the green dot, we're going to penalize this conformation that we found with as long as this energy is lower than the crystal, in order to push this minimum, the minimum of this conformation, above the energy of the experimental complex. So in order to have something like this, we're going to push. So this is where the self-learning start. Initially we start with a simpler regression with the data in the gray columns, the experimental energy and the X-ray coordinates. We're going to parameterize a first scoring function. With this scoring function, we are going to do docking, and for those cases where the global minimum is not the correct one, we're going to record this coordinate and put in a database and use it to push the energy above this value. So we are going to with this new data, we're going to generate another scoring function. We are going to refine our scoring function, and we're going to get another set of minimum. And if we are in the same situation, we are going to put those bad or decoy structures in our database. So all in all, what we are going to do is to minimize now this energy, this function. The first term is the term of the regression that you already saw. For all the crystal structures, we are going to minimize the difference between the experimental and the calculated energy. The second term is we're going to minimize the forces on the system. So for all the X-ray data, the system is in a minimum. We are going to force to be in a minimum. And the third term is the term that will grow with the cycles of the procedure, and is going to take into account all the situations where we found pose coordinates that with lower energy than the global minimum at the time. And we're going to add a fourth term that is the regularization of the system. That is just a function of parameters in order to limit the exploration of some of the parameters where we know that are physically not sound. So here how we apply our procedure. We start with the data set, experimental data and energy, and a set of parameters that will be, in the first step, will be just a random sampling of the parameters. We're going to go to the left. So here I'm referring that we took these coordinates X and energy E and the parameters, and with a program that we developed in Julia, we're going to optimize this function in pink, and by this optimization we found another set of parameters. With these parameters, we are going to do the docking. We're going to the right. We do the docking with our program that we call Binardo, and the output of this program will be a different set of coordinates and energy. Is basically a realization of the new energy surface defined by the parameters. So in these coordinates, we are going to increase our data sets with the bad examples, the times that the energy, the minimum, the global minimum, is not coincident with the minimum in the X-ray structure. So what are we using of AI? We are using automatic derivatives. We have to, in order to optimize parameters and coordinates, you have to have derivatives, and the automatic procedures is very convenient because you don't have to write down every time your equation. You can change easily your scoring function, and the derivatives will automatically be derived. We are using the batch annealing procedure that is also part of it gives the searching of the parameters a global character. You do a global search with batch annealing. and we are using the reinforcement learning. So every bad example obtained in the generation and is going to be used in the next generation in order to improve the procedure. So the batch annealing is we call it batch annealing. Is the batch procedure is just not to use the whole data set to do the minimization, to do the training or your scaling function, but just use a small subset. With this, you gain a global character in the search, because every time you do a minimization, you do we call the value step here. You are changing the data set that you actually do the minimization. So this way the parameters are jumping over examples, and it is going to at the beginning we use a small set of examples, maybe 10 examples, and as the optimization proceeds, we are gradually increasing the number of examples that we use. So at the first time, the parameters jumps across the examples and go it acquires a Monte Carlo-like procedure. So you see at the beginning here, you can see mostly, if you see, for example, here we change the size of the training set. Here we change it again, we increase it again. Here we increase it again, and so on. And with every step with every increase in the size, you can see that the fluctuation of the error is decreasing. So this is a kind of the simulating annealing in the physical methods, and we call it a batch annealing. So we have the actual optimization that is in black, and in red you have the full training data set. Yeah, just it's not optimized on the full training data set, but we use it as a control of what is going on with the system. So you see that the size increase, the both try to converge. We never, with the batch, we never go beyond 50% of the training data set. So this is a very powerful procedure to optimize, to find a global minimum, in this case of the parameters of the scoring function. Is so powerful that if you repeat two runs, your parameters are quite converged. So these two here we have the result after the simulation converge. Two different simulations started from very different random points, and the values of these parameters that we call long range is not important what it means right now, but this is a parameter as of the atoms as a function of the atoms. So you see that all acquire the same value. So this is a powerful convergence, global convergence. What about what really matters to us? That is, you obtain a good docking scoring function starting for parameters randomly choose Well, the answer is yes, you can obtain this. And the form, the way it is reached is in, you can see, you can understand the procedure here if you explain how the system evolves. So you start in the first point, you don't do any docking, you just optimize the correlation between the energy, experimental energy, and the crystal structures. So you have a very high Pearson correlation between the predicted energy and the binding energy. When you parameterize in this way, the scoring function you get is quite bad. You only have the less than 50% of the global energy minimum as near the real minimum, the minimum of the crystal structure pose. But when the cycles increase, that means you have more and more decoys, you have more and more bad examples, you are exposing to your scoring function to more and more bad examples. The system starts to learn where to go in order to make the global minimum the crystal structure. So, and this is at the expense of a lowering in the Pearson correlation coefficient. You, in the first point, all your parameters need to adjust this term, but as the system, then the docking starts to compete with the correlation, and the Pearson correlation coefficient goes down, but it goes down not by a large margin, and the docking increase. So when we have a plateau in the number of decoys that we get, we stop the procedure, and we have a scoring function that is able to not only recover the energy of the crystal structure, but also have a minimum in the X-ray structure in near 85% of the cases. So with what we have learned in this in developing this technique, well, first you have to be careful for what you wish for. This procedure, this optimization is powerful, and if you ask to minimize a thing, it will find a way to minimize, but maybe put you in a place where you don't want. For example, here is a typical situation that we have found, that in some cases the atomic radius, for example, of some parameter that you are going to optimize, it have a flat surface with respect to the error, whatever error it is. So if you go to the extreme to optimize this to the very bottom, you maybe found yourself in a situation where the radius have values that have no physical meaning, and near this near in terms of error, but maybe long away from in terms of the value of the radii, you have a zone with values that are compatible with the physics. So if you do the full optimization, you maybe end up with a better energy, but in a place with no physical meaning for your scoring function. So you need to regularize, to apply regularization and put all the physics and chemistry that you know in your system in order to limit the zone where to explore, because you will always find a minimum with this procedure. So here with these circles, I'm trying to represent a situation where, for example, if you are trying to, your data only limits the distance of the atoms. You cannot distinguish between these two situations: the gray atom, the dark atom, big with big radii, and the lightweight atom with small radii, or the other way around. These two situations have the same distance, but the parameters of the atoms are totally different. So you need to regularize your system. You need to apply all the physics you have, and of course this is common to every EI method. You need to clean your data, because anyway you maybe end up applying parameters to explain the outliers more than the bulk of the data. The cleaning of your data is always quite important. Well, this is all I have to tell you now. I would like to thank Rodrigo for the collaboration and the institutions that found our work.
Thank you very much, Marco. It was really a great talk, and thank you for sharing as fast as I could figure out. It's unpublished data, isn't it?
It's in place. It's right. We're working right now on this. Yes, it's unpublished.
Thank you very much. Now we're going to open for questions. If anybody would like to have any question, and if people want to ask the question in Portuguese, I can translate it to Professor Marcos, but most likely he's going to understand Portuguese.
Yes. If you talk slowly, si fala devagar, puedo entender.
Okay. Any question, people? Professor Camp, if you have any question, feel free.
Sem falta. Bom, eu vou aproveitar e fazer a pergunta em espanhol.
Ah, muy bien.
I knew that. Go ahead.
No, mi duda es la siguiente. ¿Por qué confiar tanto en las estructuras obtenidas por rayos X del PDB? Porque uno sabe que esas estructuras, ¿no? Ellas son cristalizadas en condiciones termodinámicas, digamos, especiales, ¿no? Si tú lo cristalizas hoy a una temperatura, una presión, unas condiciones, vas a obtener una estructura y mañana pues puedes obtener otra, ¿correcto?
Sí.
¿Por qué confiar tanto en las estructuras de...?
Sí, totalmente de acuerdo. Primero, tampoco es que varíen tanto. I'm sorry. So I don't think that they vary a lot between conditions, but they really vary. Well, what Professor Campos is saying is that crystal structures are often obtained at the temperature of liquid nitrogen, so it's not relevant at all this temperature in a biological system. But there's sufficient information that what you obtain is a minimum, a very cold minimum, but the system in the at room temperature we're going to to vary around this minimum. So this minimum is really representative of most of the conformation, or most of the geometry that you will find in at room temperature. And the other reason is that it's the only way you have to catch for a geometry in the system with the level of detail that you need to for the parametrization of a current function. You can go with NMR, for example, but in that case you don't have the resolution that you need to put every atom and every distance in your function. So we account for this but when we in this graph, in the blue graph, that it say the percentage of time that your scaling function have a minimum in the near the crystal structure is the key. The key is near the crystal structure. You allow for a margin. You usually use a 2 Armstrong margin to count for a success. If your answer is near 2 and RMSD of less than 2 Armstrong, you count for a success. And in this way, you allow some freedom, some indetermination in the coordinates of your system. I don't know if that convince you, Professor Campos.
No, I like it, your answer, but I am not convinced.
Okay. Maybe we can talk later about it.
Hopefully he's not going to be the referee of your paper.
No, this is not something that we came up with. This is a very standard procedure to use the X-ray structure and to allow for a margin of error of this structure that you know that this structure have. So I'm not worried about that. But I would like to talk about this with the professor.
Any other question, people? So if people don't have, I'm going to make a few questions. First, you have the same question that I was thinking about. So now I have two questions left. I don't know if you have this information, Marcos, but Vinardo has now 215 citations. Did you know that? Do you know that?
I knew that it is going very well, but I don't know the exact number and never knew.
Congratulations for that.
Thank you.
Vinardo is a program that was developed by Professor
Marcos
Villarreal and Rodrigo. It's still using them. And my question is exactly about Vinardo. You are going to have the version 2 of Vinardo?
Yes, with this procedure we're parameterizing the version 2. I think that this is a more robust way to parameterize things, and maybe this guy here is the new Vinardo.
I see.
The parameters behind these results are the new Vinardo.
I see. And hold on this slide, please. This data you have is for the test set or the training set?
It's a very good question. Right here is just the training set. In the test set, we have very similar results, but as right now we are just using small data sets, the results vary a lot between data sets, because as you know, some For example, with the Pearson correlation, it depends on how the data is spread along the values, the experimental values, is how the Pearson correlation changes a lot. If you happen to use a data set with a very narrow range of experimental values, naturally the Pearson correlation will be low. So there is in a small data set you have a lot of fluctuations. We need to go to larger data sets to have a better picture of the training and testing results. But yes, that's a very good point to take.
Thank you. Only to complete the Professor Camp's question. So, from what I understood, your crystal structure without any minimization. That's true?
Yes, crystal structure without minimization. Yes.
Yeah. A couple of weeks ago, I wrote a review, and I was checking the data at the PDB, and you have another techniques as NMR, cryo-EM, and neutron diffraction. And if you focus on structures, protein structures with the ligand for which you have binding affinity data, you have over 98% of the structures available at the PDB, they are from X-ray diffraction crystallography.
Yes, because the degree of detail that you have with this technique is not available by any other technique right now, and you really need to have all the atoms defined and all the distance defined in order to be useful for this calculation. So I don't think that how we could replace the data of the X-ray data.
Most of my former years as research was as crystallographer, and I'm old enough to have the opportunity to work with no cryo crystallography. My first structure didn't use cryocrystallography. Then I solved the same structure with the frozen crystal and unfrozen crystal, and I superposed the two structure. They are exactly the same.
Listen, yes. It's in the worst case, it's a good approximation. The cryo structure is a good approximation, but in most cases, it's almost exactly. I have experienced a lot of experience with MD simulation of ligand proteins, and if you believe in the MD simulations, they're always around the crystal structure. They don't jump around at any place. They stay near the crystal structure. So maybe it's the same bias. I don't know. It is possible.
Okay. Any other questions? Okay, Professor Marcos, it was really a pleasure to have you here, and thank you very much in name of the University, the Federal University of Alfenas, and also in the name of a post-degree program in Física. You have here the coordinator of the course. If you want to say something, you can also share the screen, Professor Camps. Okay, so thank you very much for accepting participate. It was really an honor, and hopefully in the next few weeks we are going to have a nice news about the acceptance of our paper.
Oh, that would be nice. Well, thank you, Walter, and your students and professor to listen this talk. It was a pleasure for me. Thank you.
Thank you very much, Professor.